A very early morning here. Not necessarily early for me. This is when I usually get up. It's Teacher Appreciation Week, and I want to spend the next few videos profiling some of my favorite teachers in my academic life. The first one I want to start with is Dr. John Kolena, who taught physics at the North Carolina School of Science and Math, which is the public boarding high school I went to for 11th and 12th grade. It's in Durham, North Carolina. So first off, so Dr. Kolena has been retired for some years now, and of course most of my teachers are either retired or dead, given my age. In any case, let me focus first on the physics I learned from Dr. Kolena. I basically took every class he taught. Now, when I went to Science and Math, and it is only a 2-year school, it's only junior and senior year in high school, I got placed in his Physics with Topics class. One of the things about NCSSM is that all the students have to take 1 full year of physics, 1 full year of chemistry, and 1 full year of biology. So I doubled up on chemistry and physics in my junior year and took biology and more physics in my senior year. So I took Physics with Topics with Dr. Kolena, and then also that first semester I took a Fractals and Chaos class, which he co-taught with a math teacher, Kevin Barkovich. So specifically with regards to the physics I took with him, and I took an astrophysics class and a modern science class, and then senior year I also did an AP physics class, which was kind of special. I think there was only 4 of us in the class, and we were selected because basically we had calculus very solidly before and had physics before, so we could use more advanced physics than, say, most of the people taking the regular AP physics class. In any case, some of the stuff I learned from physics, and one of the big things, of course, is I ended up majoring in physics in undergraduate. Now, you'll notice I don't do physics currently. Most people who get degrees in physics don't do physics in any meaningful way, and a lot ended up in finance. There's a reason for that, but that's not for this video. Some of the things I learned, dimensional analysis, which has to do with looking at units. You're trying to see what formulas, physical laws or whatever, seem to make sense given first principles, units, and that sort of thing. I learned about approximations. You know, sine theta is approximately equal to theta, and that's the first order polynomial expansion for sine of theta around theta equals 0. Let's see. I mean, obviously, I learned regular Newtonian physics. I learned special relativity. I learned very little with regards to general relativity. I learned some quantum weirdness. I learned, a lot of really interesting physics, and part of why I went on to major in physics is that Dr. Kolena had told us about some of the open questions, the things that were still left. And as far as I know, they still are left to be explained in physics. One is, what is dark matter? And then the question is, of course, is there really such a thing as dark matter? Do we just not understand gravity all that well? And that's my take, is we really don't know gravity very well. Where are all the neutrinos? The one that really sticks in my mind is, how do we go from that quantum weirdness? And we had some great discussions on Schrodinger's cat in class. The consensus of the class is that the cat would know. That's not exactly how it works. But we got to read stuff like quantum reality and some other fairly accessible quantum books where we didn't have to get all into the linear algebra, bracket notation, the partial differential equations and Schrodinger's equation and all of that. For the wave function, that I got to do in undergraduate. But we got a taste, and we got interpretations, and we understood. And one of the big takeaways from the physics classes where sometimes we just don't know. And the other explanation is that's just the way it is. It's like, how does it work that way? And I remember one student in particular. So Dr. Kolena is quite a character. Anytime we'd say something stupid, eye roll and a smack. Sometimes he threw chalk and erasers at us. It didn't happen all that often. And, you get good at dodging, and if you don't, getting hit by an eraser is no big deal. Yeah, he'd probably be, fired or something nowadays. I don't know. It's bullshit. Anyway, it was very funny. But I do remember a student when we were doing special relativity. And of course, this is the weirdest thing. Usually you go to Newtonian, and special relativity is really just the logical conclusion with dealing with a constant speed of light and a Newtonian physics. So this isn't even quantum weirdness, as it were. Nothing very strange. Doing special relativity, and our minds are boggling over it, and it is pretty mind-boggling. And one student she decided she didn't believe it. Like, how can you not believe it? There is experimental support. Yes, we understand it's not intuitive, but we generally aren't looking at near speeds of light in our day-to-day lives. Now, there is a series of essays, Mr. Tompkins, and I think it's by George Gamow, which tries to show you what it would look like if the speed of light were, say, something like 100 miles per hour, as opposed to what it really is, and how weird that would be, and also similarly Planck's constant and some other stuff that were at fairly small levels. In any case, she decided she didn't believe it. However, I don't know what her grades were, but she did do the special relativity problems as, we set up and do our frames of reference and that kind of thing, but she just didn't believe it. It was very funny. So that's all the physics stuff. And as I said, I did fractals in CAS. But okay, so what's the pertinence to my life now? Obviously, I don't do physics now. I barely read any physics now. The only crap that I see from time to time. I mean, there's Higgs boson, but I really don't care about a theory of everything. And then there's string theory, and I don't want to go there. It was the other stuff. So I really learned how to do problem solving. And one of the things I remember him telling us is to draw a picture of, now this, of course, you're thinking force diagrams, and that's true. But the way I interpret this more generally is visualize it, okay? And visualize the problem. And that's how often I do, or I have to do a lot of data analysis. So that's, more or less what I do as my main job. And a lot of times things become clearer. I can see anomalies. I can see trends. I can see it. I graph it. I can visualize it. I might see a strong correlation. Well, let me graph it. There's something called Anscombe's quartet, and I think there's the Datasaurus Rex, which is also very popular. You can have very different sets of data which have the same, say, means and standard deviations and correlations even, and have very different shapes. So visualize it. That's very important. The second one, and this I use in my spreadsheets all the time, you test boundary conditions. And what I mean by this is not a differential equation where you have to get the boundary conditions to match up. And if you don't understand what I just said, it doesn't matter. So let me give you an example from basically first semester physics, where you're doing force diagrams. You have an inclined plane and a block on the plane. And what's keeping that block from just sliding down the plane? Well, it's friction. So you have this coefficient of friction and mass and blah, blah, blah. So what you are trying to find is the critical angle. And you can do this, you could do some very simple experiments to test this. It's like, okay, you have an angle theta, and you're going to just keep increasing that angle until the block starts to slide. Okay? So we need to test, what if the critical angle, what does it mean if the critical angle is 0? It just starts, and basically that means that a little epsilon greater than 0 goes whoosh. That's a frictionless plane. What if you have to go to a right angle, so before it slides? Well, that's like infinite friction. Does that make sense? Yeah, that does make sense. I have to do that sort of thing on spreadsheets because often there are natural boundaries. For example, probability has to be between 0 and 1. It's always a good idea, and I actually did this, the first annuity calculator I wrote, I had as my boundary conditions, and I still do this from time to time, is everybody dies at the beginning of the year or everybody dies at the end of the year. And of course, something in between is the real answer, but it gives me bounds of what my answers are going to be. So I look at those boundaries. I need to make sure it works. Sometimes the boundaries aren't really boundaries. One of the things that we kept running into, so I am on a project oversight group for an interest rate generator that was originally developed at the American Academy of Actuaries, and the regulators took it over, and then the Society of Actuaries took it over, and we'll just leave it there. That said, one of the things this generator does not do is support negative interest rates. Now you might think, well, that doesn't make any sense. However, there are actual Bank of Japan, and there's some real negative interest rates, and even nominal. I mean, real from an inflation standpoint, people understand that, but a nominal negative interest rate, yes, they can exist. So that's some of that. And then the biggest experience I had with Dr. Kolena, well, I had a challenge for the first time in a long time. Okay, I don't want to get into my relationship with school right now, but for the longest time, I wouldn't answer in class unless basically forced to, because if I knew the answer, and often I did, what was the point in answering? I knew the answer. Why not give somebody else who wasn't quite sure? I mean, because this isn't about showing off. It's about confirming that you are correct. Well, when I was in this regular physics with topics, I didn't even know. I hadn't done any physics before. I had no idea. So I actually tried to answer questions, and I often got it wrong. I often replied wrong. And what's hilarious, and this is what I tell students later, some of my classmates, and I think it was senior year, not at a reunion, like we were just hanging out or something, like, oh, you're always right. In class, I'm like, no, I'm not. Well, I'm the one who's noticing every time I'm wrong. But other people weren't. They were noticing that I was willing to answer. And I was right. I wasn't wrong all the time. So I will say that. I wasn't wrong all the time. But they weren't really keeping score of how accurate I was. I was keeping score, and that was good from an intellectual humility standpoint. But you shouldn't be afraid to be wrong in school. That's the whole point. You're there to learn. And I learned a lot from Dr. Kolena, because I was not afraid to be wrong, and I was often wrong, and I got corrected. And when you're wrong and you think, and you're like, oh, okay, that was one big thing. And the other one did not come from physics, though he got there eventually. In the first year in the physics with topics, he didn't really give us many of the open physics things. It wasn't until my senior year, and I was taking the more advanced courses. Because like in Newtonian mechanics, you're not going to run into that, or even electromagnetism. It's more of the general relativity and quantum stuff that, and particle physics that you're running into that. So I took a fractals and chaos class. And so it's a math class. It's nonlinear dynamics. It's fractal dimensions. It's all of that jazz. And some of it was well developed. And often they would give us a homework that we'd have a week to do, and we'd come back and be like, we couldn't answer it, blah, blah, blah. And then Kolena and Barkovich would tell us, oh, well, it's an open research question. Why did you tell us that before? But the big lesson there was the answer is not always in the back of the book. That's number one. So that was a great lesson. When you're at a school like NCSSM, most of the students are used to being the best in science and math. They're used to always having an answer, and a very definite answer. And sometimes knowing that, the answer isn't known, and then sometimes there might not even be an answer. So that's really inspiring in terms of wonder and a goad to research. Go and find out. There is stuff still to be found important stuff still to be found. Now, and we might not be able to find it. That's something to think about. When I got to undergrad and I was doing some grad level classes and we got questions like that, I was appalled when graduate students in the class were complaining that they were given open-ended questions. I'm thinking, what are you in graduate school for? Isn't this the kind of thing you're supposed to be doing? But I got a taste of this in high school, and the earlier you can get a taste of that. This is for people, in academic life. I think it's a great thing. The earlier, the better, though, of course. In elementary school, everything's a wonder. Everything is new to you. But by the time you get to high school, you don't want science and even math to be presented to the students as it's all settled. There's nothing more to find. It's just going out to that millionth decimal place. That's not really going to inspire anybody to do anything in science and math if you think it's all been figured out already. So giving them a taste, and they don't even need, there's a lot of stuff, a lot of important stuff. I remember Fermat's last theorem was still open at the time, but it's not open anymore. But there's still a lot of accessible problems, both in math and in physics. I don't know, I can't speak to chemistry or biology or other sciences. But, teachers, it's not teach the controversy, teach what's left to be found. And this is something, I've carried with me. There's a lot of things that I have salted in the back of my mind and are just bubbling there. Maybe I'll get an answer one day, and maybe I won't. But, it's a lot of fun looking for it. So here's to Dr. Kolena, my best teacher ever.